Hello students, in this class I am going to teach you Lorentz theorem. In earlier classes we saw Cauchy's integral theorem and Cauchy's integral formula, what is the meaning of analytic function, and we saw some of the problems related with analytic functions, then Cauchy-Riemann equations, proof, statement, etc. If you have any doubt, kindly clarify all my earlier videos in the respective topics. So before starting Lorentz theorem, we should know what is the analytic function. So analytic function is a function which satisfies CR equations. We know what are CR equations. Now we will see what is the statement of Lorentz theorem. For Lorentz theorem, when it is applied, what is the condition? That is, when there are two concentric circles, one circle is C1, another circle is C2. C1 circle is the big circle and C2 will be inside that circle with the center A. So for this smaller circle, the radius is R2. For the bigger circle, the radius is R1. That is, for C1, radius is R1. For C2, radius is R2. Now you see the statement. Suppose a function f of z is analytic in the closed ring bound by two concentric circles C1 and C2 with center A and radii R1 and R2, where this R2 will be lesser than R1. R2 is less than R1. Okay, this is the statement. So what will happen if Z is any point in the annuals? If annual means the space between the two circles is called annuals. So if we are making a point Z may be anywhere, and what will be its value? Then that time, according to Lorentz theorem, f of z is equal to summation of n is equal to 0 to infinity a n z minus a whole power n plus summation of n is equal to 1 to infinity b n z minus a whole power minus n. So this is the Lorentz equation. Here a n is nothing but 1 by 2 pi I integral of C1 f of t minus a whole power n plus 1 into dt, where n will be 0, 1, 2, 3, 4, etc. Similarly, the bn is the another constant. Its value will be 1 by 2 pi I integral C2 f of t minus a minus n plus 1 into dt, where n is equal to 0, 1, 2, 3, 4. So, Lorentz theorem statement is, suppose a function f of z is analytic in the closed ring bound of two concentric circles C1 and C2 with center A and radii R1 and R2, then if z is any point of the annuals, according to Lorentz theorem, the function f of z will be equal to summation of n is equal to 0 to infinity a n z minus a whole power n plus summation of n is equal to 1 to infinity b n z minus a whole power minus n. Then we will substitute what will be a n and b n are two constants, and a n will depends upon the annual C1, circle C1, and b n will be depends on circle C2. Okay, now this is the statement. Now we want to prove the Lorentz theorem. For that, proof. For that, we know Cauchy's integral formula for multiple closed circles. So, according to Cauchy's integral formula for multiple circles, f of a should be is equal to 1 by 2 pi I if there are two circles, so C1 f of z minus a into dz minus 1 by 2 pi I circle C2 f of z divided by z minus a into dz. Let it be equation number 1. So we know that Cauchy's integral formula for one circle is f of a is equal to 1 by 2 pi I integral of C1 f of z divided by z minus a into dz. We are having two circles. So for multiple circles, Cauchy's integral formula is f of a, that should be is equal to 1 by 2 pi I integral C1 f of z minus a into dz minus, for another circle, 1 by 2 pi I integral C2 f of z minus a into dz. Okay, so this is, let it be the equation number 1. Now substitute a is equal to z and z equal to t in equation 1. So substitute a is equal to z and z is equal to t in equation 1. So equation 1 becomes f of z, that is equal to 1 by 2 pi I integral C1 f of t, instead of z you substitute t, so f of t divided by z minus a, so t minus z into dt minus 1 by 2 pi I for another circle C2 f of t divided by t minus z into dt. Now f of z, that is equal to 1 by 2 pi I integral C1 f of t divided by t minus z dt. In this we will change this plus sign, so here z will come to here, t position, t will go to this position, therefore this sign will become, minus sign will become plus here, so 2 pi I close the circle of C2 f of t z minus t into dt. Now you keep this equation number 2. Okay, right. Now add and subtract a in the denominator of equation 2. In the denominators of equation 2. So equation 2 becomes, what will happen now? F of z, that is equal to 1 by 2 pi I integration of C1 f of t divided by here t minus a plus a minus z into dt plus 1 by 2 pi I integral of C2 f of t z minus a plus a minus t into dt. Okay, understand now? So I am adding and subtracting minus a in the denominator just for our convenience. Now I will separate this f of z, that is equal to 1 by 2 pi I summation integration of C1 f of t divided by, to separate it, separate t minus a minus z minus a into dt plus 1 by 2 pi I integration of C2 f of t divided by z minus a minus t minus a into dt. f of z, that is equal to 1 by 2 pi I closed integral c1 f of t divided by, I will take this t minus a outside, so t minus a into, when you are taking out, then 1 minus z minus a divided by t minus a, okay, into dt. Then the second term, now the second term becomes plus 1 by 2 pi I closed integral c2 f of t divided by, here you will take z minus a outside, z minus a, when you are taking out, it will become 1 minus t minus a divided by z minus a. T minus a, 1 minus t minus a divided by z minus a into dt. Make this equation number 3. Okay, so it is clear. So I am taking out this t minus a, that's all. So when I am taking t minus a from this equation, what will happen? T minus a will come out, means it becomes 1 minus z minus a divided by t minus a. Here I am taking z minus a out, therefore 1 minus t minus a z minus a into dt. This is equation number 3. Now to solve this equation number 3, I am keeping this separately. This is 1 by 2 pi I closed integral c1 f of t minus a 1 minus z minus a t minus a into dt as L1, and this function is L2. Okay, in equation 3 we will substitute two parts. That is, one part is that L1 is equal to 1 by 2 pi I integration of c1 1 by t minus a into 1 minus z minus a divided by t minus a whole power minus 1 f of t dt. So you keep it equation number 4. Then let equation L2, that is 1 by 2 pi I for the second circle c2 1 by z minus a into 1 minus t minus a divided by z minus a whole power minus 1 f of t dt. This is equation number 5. So we divided equation number 3 into two parts. One is L1, another one is L2. Now to solve L1 and L2, we will use binomial expansion. Binomial expansion. So what is binomial expansion? If there is a function 1 minus x whole power minus 1, then we should write according to binomial expansion 1 plus x square plus x cube plus etc. So this is binomial expansion. Now we will apply here for L1. So in L1, let it be x is equal to z minus a divided by t minus a. We will keep it as x. You see, this is 1 minus, if this term is x, so 1 minus x whole power minus 1. So we will expand in this way, 1 plus x square plus x cube plus etc. So now in equation 4 becomes L1, that is equal to 1 by 2 pi I, according to binomial equation, integral c1 1 by t minus a, then expansion is 1 plus x. X here is z minus a. So z minus a divided by t minus a is x. So x plus x square z minus a divided by t minus a the whole square plus z minus a divided by t minus a whole cube plus etc etc into f of t dt. Okay. Now 1 by 2 pi I c1. You multiply this t minus a in the denominator everywhere. So when you are multiplying, what will happen with this 1 means it is 1 by t minus a, then plus z minus a, t minus a into t minus a becomes t minus a the whole square, plus z minus a the whole square divided by t minus a the whole square plus t minus a into t minus a, then it becomes t minus a the whole cube plus z minus a the whole cube divided by t minus a the whole power 4 into f of t dt. Now you multiply this f of t dt inside. So 1 by 2 pi I integral c1 f of t dt divided by t minus a plus then closed integral of c1 f of t dt divided by t minus a the whole square into z minus a plus c1 f of t dt divided by t minus a the whole cube z minus a the whole square plus for the third term c1 f of t dt divided by t minus a the whole power 4 into z minus a the whole cube. So we multiplied these things. Now you multiply this 1 by 2 pi I throughout. So we will get 1 by 2 pi c1 f of t dt divided by t minus a plus c1 z minus a divided by t minus a the whole square f of t dt plus c1 z minus a the whole square t minus a the whole cube f of t dt plus z1 z minus a the whole cube divided by t minus a the whole cube f of t dt. Now 1 by 2 pi I c1 f of t dt divided by t minus a plus z minus a into 1 by 2 pi I c1 f of t dt divided by t minus a the whole square plus z minus a the whole square into 1 by 2 pi I c1 f of t dt divided by t minus a the whole cube plus z minus a the whole cube into 1 by 2 pi I c1 of f of t dt divided by t minus a the whole power 4 into z minus a the whole power 4. And no, here z minus a came out, so this is. Now to make this equation for a common form, let L1 is equal to summation of n is equal to 0 to infinity z minus a whole power n 1 by 2 pi I integral c1 f of t dt divided by t minus a n plus 1. So this above equation is equal to this thing. How? Now you put n is equal to 0. So z minus a whole power 0. Anything power 0 is 1. So remaining is 1 by 2 pi I closed integral of c1 f of t dt t minus a. Here n is equal to 0, so it becomes 1. So t minus a. So it represents the first term. When n is equal to 1, substitute here z minus a into 1. So z minus a 1 by 2 pi I f of t dt t minus a. 1 plus 1 is 2. So it comes t minus a the whole square. So second term. Similarly, you are substituting n is equal to 0, 1, 2, 3, 4, etc. We will get the corresponding terms. Therefore, this whole equation we will write it as L1 is equal to n summation of n is equal to 0 to infinity z minus a whole power n 1 by 2 pi I closed integral of c1 f of t dt t minus a n plus 1. Now, put an that is equal to 1 by 2 pi I c1 f of t dt divided by t minus a whole power n plus 1. So, substitute a coefficient value of an which should be is equal to 1 by 2 pi I integration of f of t dt divided by t minus a whole power n. So, for this term I am substituting as an. Therefore, L1 becomes summation n is equal to 0 to infinity z minus a whole power n into an. Okay. So, this is equation number 6. So, we derived the value for L1. In similar way, we should calculate for L2 also. We know L2. Now, the equation number 5. From equation number 5, L2 that is equal to 1 by 2 pi I summation C2 1 by Z minus A. You expand according to binomial theorem 1 plus T minus A divided by Z minus A plus T minus A by Z minus A the whole square plus T minus A divided by Z minus A the whole cube plus etc. into f of t dt. Here in equation L2, for L2, x value should be t minus a divided by z minus a. That is why you are expanding instead of x. This is x square, this is x cube. So, by applying a binomial theorem, we are expanding this. So, L2 is equal to now 1 by 2 pi. Same procedure what I have did for C1. C2. Now I am multiplying here inside 1 by z minus a plus t minus a divided by z minus a the whole square plus t minus a the whole square divided by z minus a the whole cube plus t minus a the whole cube divided by z minus a the whole power 4 plus etc. into f of t dt. Now, you multiply this 1 by 2 pi I everything inside. So, what we will get as usual 1 by 2 pi I C2 multiply this f of t dt inside. So, f of t dt divided by z minus a plus C2 t minus a divided by z minus a the whole square f of t dt plus C2 t minus a the whole square divided by z minus a the whole cube f of t dt. The last term will be C2 t minus a the whole cube divided by z minus a the whole cube f of t dt. Now multiply this 1 by 2 pi I inside. So 1 by 2 pi I, you take it 1 by z minus a is also outside So the remaining is, for the first term, it is f of t dt plus 1 by 2 pi I 1 by z minus a the whole square c2 t minus a divided by t minus a into f of t dt. For the third term, 1 by 2 pi I 1 by z minus a the whole cube c2 t minus a the whole square f of t dt. Then for the fourth term, 1 by 2 pi I into 1 by z minus a the whole power 4 closed integral of t2 t minus a the whole cube f of t dt. Now for these equations, I will make a common equation. I want to make a common equation as I have did for L1. So this L2, how we will make it common? L2 that is equal to, this common equation becomes sigma equal to, sigma n is equal to 1 to infinity z minus a whole power, otherwise z minus a whole power, this is 1 by z minus a whole power n 1 by 2 pi I c2 t minus a n minus 1 f of t dt. Now when n becomes 1, this term becomes z minus a whole power 1, that is 1 by z minus a into 1 by 2 pi I, some closed integral of c2 t minus a, n is equal to 1, so 1 into 1 is 1 minus 1 is 0, so this term becomes 0, then f of t dt, which represents the first term of the above equation. Similarly, when n is equal to 2 you are substituting, then 1 by z minus a the whole square into 1 by 2 minus a into summation of c2 t minus a, n is 2, so 2 minus 1 is 1, so t minus a f of t dt, it represents the second. Similarly, third, fourth, when you are changing the value of n. So common we can write as L2 that is equal to, n is equal to 1 to infinity. Since this is in denominator, when it goes to numerator, then this term becomes z minus a whole power minus n into 1 by 2 pi I closed integral of c2 t minus a n minus 1 f of t dt. Now similarly, we will introduce another constant bn, that should be is equal to 1 by 2 pi I c2 t minus a n minus 1 f of t dt. So substitute this value bn here. Therefore L2 is equal to summation n is equal to 1 to infinity bn into z minus a whole power minus n. So this is equation number 7. So we found out for the value of L2. So now we know L1 and L2. Therefore the equation 3 will become, it is the combination of L1 and L2. Therefore this equation becomes, 3 becomes f of z that is equal to L1 value from equation number 6. We know n is equal to 0 to infinity a n z minus a whole power n. From the equation 7, we found out for the value of L2, that is sigma n is equal to 1 to infinity bn z minus a whole power minus n. So here what we are doing, substituting the values of L1 and L2 from equations 6 and 7. So we get the final result of Laurent's theorem f of z, that is equal to summation of n is equal to 0 to infinity a n z minus a whole power n plus summation of n is equal to 1 to n infinity some bn into z minus a whole power minus n. So hence we proved Laurent's theorem. Okay, hope you all understand the statement as well as proof for Laurent's theorem. Thank you.